Okay, great. We are very happy to have Arpit Das from University of Edinburgh as our next speaker. Please.
Thank you so much, and thanks all for coming to this session. So my talk is going to be about non-invertible symmetries, which is this new reformulation of symmetries as we think in QFT, and some entanglement properties of it in the context of two-dimensional conformal field theory, especially rational conformal field theories. So this is a work done with this wonderful set of collaborators, and it's based on this paper which came out like 6 months ago, and an upcoming work which will probably be out in a couple of days. So let's get started. So let's say we have a two-dimensional rational conformal field theory. And by rational conformal field theory, I mean where you have a finite set of primaries with respect to some chiral algebra. And furthermore, let's assume that it's a diagonal theory. So it means we have a diagonal modular invariant partition function. So then we can classify the primaries as irreducible representations of the chiral algebra of the theory. And so I'm denoting the primaries as phi. And in this way, you can write down the Hilbert space of your primaries as a sum over your Verma modules, where each Verma module correspond to one of the primaries and then its descendants. And then here there is a picture of the torus partition function, which is modular invariant, and it can be expanded in terms of holomorphic and anti-holomorphic characters corresponding to these primaries. So with this much information, it was John Cardy who showed us that if you are now interested in the entanglement entropy of some interval A of length L, then you can consider some kind of factorization, assuming that such a factorization is possible, between the region A and its complement, and then you can compute the von Neumann entropy of this interval, which will give you the entanglement entropy of that interval. And it turns out that at leading order, it just depends on the central charge of the theory. And this L is the length of the interval, and this epsilon takes care of UV divergences which you may encounter at these entangling points. So this is a very well-known result, and the way Cardy derived it was using the replica trick. However, he then quickly showed that we can do something more. So there is something called a boundary conformal field theory approach to deriving this Cardy formula. So what Cardy taught us is that, so let's again look at this interval of length L, and then you introduce some small circles or disks of epsilon radius, which is your UV cutoff, and then you demand that this geometry that you are now creating is conformally invariant. So that's why you impose some boundary conditions at these entangling points, and they have to be conformally invariant boundary conditions. And then the idea is that you replicate this manifold n times, just like we do in the usual Cardy case, and then you conformally map it using a conformal map where this tau is your torus parameter and this w is length of this annulus. So then you go from this picture to an annulus, where at the entangling surfaces you now have these conformally invariant boundaries, which are also called Cardy states after Cardy. And in a diagonal rational theory, these are in one-to-one correspondence with your primaries in the theory. So with this picture in mind, so where you go from this torus with an interval inserted to an annulus, we can again look at the factorization. And now the Hilbert space factorizes into again these two components, A and its A complement, but restricted to satisfying or having these conformally invariant boundary conditions at the entangling points. And with this, we can define something called annulus partition function, which is again the same torus partition function, but respecting these boundary constraints coming from the conformally invariant Cardy states. And now this modular norm Q is expressed in terms of tau, which is related to this annulus width in this way. And with this, moving on, now you can do the usual trick. So you can just compute the von Neumann entropy with this parameter. So you compute the nth replicated partition function, take its analytical continuation, and so this is exactly how the replica trick follows from Cardy. And then the thing to compute is this partition function here with respect to these boundary constraints, and so you can expand it in terms of characters. So often people say that this point of view is like the open string point of view. I shall discuss it in the next slide more. And then by S duality you can transform it to the closed string picture, where now it computes the transition amplitude between two twisted states. And then if you take the high temperature limit, then you can find the overlap between these twisted states with respect to the vacuum, and you get to leading order an answer like this, which you can clearly see that if you now take the log of this and take this limit, you end up with the Cardi formula at leading order, which goes as the central charge of the theory. So going back again to this open closed thing, so on the left hand side we have this open picture, and if you do an S duality, then it transforms into, so this trace transforms into a propagation amplitude between these closed string states alpha and beta. So in that way you can compute this overlap of such closed string states, and you then replicate and then get the von Neumann entropy from that. So that correctly reproduces the Cardi result, that at leading order it goes as central charge of the theory, and with a log piece which is controlled by the UV cutoff. Additionally, you have these terms which essentially comes from the overlap of these closed string states with respect to the vacuum of your theory, and these overlaps are something known as Affleck-Ludwig boundary entropy. So these are positive functions, and then you, so these are at order 1 or constant pieces, and then you have higher order subleading terms. So this is another way to obtain the Cardi result using the approach of boundary CFT, and we will soon see the importance of this approach. So the idea is that okay, we know about entanglement entropy of this interval. Now we want to ask this question, that suppose we have some external, suppose we have some more internal symmetries on top of conformal symmetry, then how does this entanglement of this line that was there, this line, how does the entropy partitions into the different charge sectors which belong to the irreducible representations of your symmetry group. So this was something which was done like 5 years ago, and we want to do it for these new kind of symmetries, symmetries which do not form a group but rather something like a fusion algebra. So before that, let's quickly review what are called topological line operators in 2D CFTs, and these will precisely give us the non-invertible symmetries. So these are also called Verlinde lines, and so this is again your torus partition function. You consider a topological line, and then this line is now inserted along the spatial direction of your torus, and then it acts on your primaries in this particular way, where these S are your S matrix. And if you want to compute the partition function with such a line inserted along the spatial slice, then you just insert the group element corresponding to this line in this trace, and then you can show that in any rational conformal field theory, such topological lines, they commute with the stress tensor modes, with all the stress tensor modes, and hence they commute with the Hamiltonian of your theory. So they indeed generate global symmetries in CFTs. Furthermore, in a diagonal theory, they follow the same fusion algebra as your primaries with positive fusion coefficients. And if from this fusion you have a group-like law, then we will call such lines as invertible, which means that there is an inverse for every line, and they pair up to identity. However, if you consider a line whose fusion is given as something like this, then such a line will be non-invertible, because there will be no inverse of that line in this set satisfying this fusion algebra. And one prototypical example is people familiar with the Ising model. It's the Kramer's one-year it's the Kramer's one-year duality, which is the n line, and if you know the fusion of it, then it's n square is 1 plus the z2 line, so it's non-invertible. So now let's quickly discuss the group-like case. So we want to compute the entanglement of this interval A, and how does it partition into the various irreducible representations of your group. So for that we need two notions. So first one is something called the G-symmetric conformal boundary. So notice that previously we had the same partition function in the boundary CFT approach, but this A was just identity. So the closed string states that we had were just conformally invariant Cardi states. But on top of that, now we further demand that these Cardi states should be G-symmetric, by which I mean that if you act it with a group element, you get back the same state. So this is a G-invariant Cardi state. So if you have such a Cardi state, then you can compute such an overlap for every group element. And you can construct the irreps of the group by using the orthogonality theorem, where this D is the dimension of the irrep and G is your group, the volume of the group. And from this you can compute something like a projected partition function which projects this reduced density matrix to each irrep. And again you play the same game, you compute the Rayleigh entropy and then take the analytical continuation, and you get at leading order that for any irreducible representation it still goes as central charge over 3. So the leading piece doesn't care about which irrep you are, and this in the literature is known as equipartition of entanglement across irreps at leading order. And so the idea is that we want to extend this to non-invertible or categorical symmetries which satisfy a fusion algebra and not necessarily a group law. So again we need two notions. So we need a notion of a symmetric state. Turns out there are two notions here. One which is called a strongly symmetric state and one which is called a weakly symmetric state. So a strongly symmetric state is the one which, when acted upon by a topological line, gives you back the line itself, gives you back the state itself with some non-negative integer. And a weakly symmetric state is something which takes the state and takes it into a sum, where the same state also appears, but there can be some more states here. So in the condensed matter terminology, the first kind of symmetric state is when people say that you can take the non-invertible category and it's non-anomalous, whereas the second thing is something which people say that you can gauge this particular symmetry. So this is about symmetric states. And then we also need some kind of projectors. So the way to construct projectors here in order to get to some irreps of such a non-invertible category is to look at projectors that map you from the whole Hilbert space to particular Verma modules, and they happen to have a simple expression just like the group case. Thank you. With that you can again compute this entanglement entropy, and it turns out that at leading order it's again equipartitioned. And here the dimension of the irreps are now replaced by what are called the quantum dimension of your non-invertible lines, and you have the familiar boundary entropy again. So let's quickly discuss an example, and with that I'll conclude. So let's look at the tricriticalizing. So it is given by these topological line operators corresponding to those primaries. Out of them, the first two are invertible. So this is the identity line, and this is the Z2 symmetry of tricriticalizing, and this is the Kramer's one here N, and then these four are non-invertible lines. So we have a group-like symmetry here, which is Z2, which is just comprising of 1 and eta. So we know that Z2 has two irreps, one-dimensional irreps, the even and the odd. So you can write down the projectors of these lines and sum them up to get the even, and these projectors sum up to give you the odd irrep. And then you can do a symmetry resolution. You get that at leading order, even in fact at sub-leading order, because the dimensions are 1, the entropy is equipartition. And there happens to be another line which is another category which is non-invertible, the Fibonacci category, and there also you can like construct the projectors as such, and then you can compute the two entropy with respect to different charge sectors. But here the interesting thing is that because the dimension of these non-invertible lines is greater than 1, here equipartition only happens up to leading order and it breaks at the sub-leading order. So that's one of the message, and that's a distinguishable feature of non-invertible symmetries. So sorry for running a bit over time maybe, and thank you.
Questions?
Can you go to slide number 8? Yeah, here. So here you say that in the weakly symmetric case, C can be gauged, right?
Yes.
And in the strongly symmetric case, it's non-anomalous.
Yes.
When you say it's non-anomalous, do you also mean that it doesn't have Tufft anomaly?
Yes.
Okay,
it doesn't have.
but if it doesn't have Tufft anomaly, then can't it be gauged?
Yes. So that's a very good question. So there's a small subtlety when you are dealing with non-invertible symmetry. So in case of group-like symmetries, what you're saying is exactly what's true. So if something is non-anomalous, it can be gauged. Okay. But in the non-invertible case, and there's some subtle aspects here we can discuss maybe later. So there, being able to be gauged is a very weak notion compared to being Tufft anomaly free. So there are lines where you can gauge them, but they will still contain some anomaly.
So, for example, there is this non-invertible symmetry which is called a rep H, where H is a Hopf algebra, and some people say that it can't be gauged unless you can extract a Frobenius algebra out of it, something like that. So, are you talking about those aspects?
Yes.
Okay.
Like precisely the example of Fibonacci that I gave. So that's a thing that can be gauged, but it has anomaly.
Okay.
So it's in spirit with what you said.
Okay. Thank you.
Thoughts for higher order terms? Can these be computed for the non-invertible?
I think the computation will exactly follow how it works for the group like case, because they are very identical in terms of the expressions that you get. However, the interesting part to me is seeing this equipartition. So when we started this work, we thought that because of this non-invertibility, the equipartition will break even at leading order, but turns out it doesn't. But definitely you can compute it.
Other questions? If no, let's thank the speaker again.